So we've discussed so far what is the primary energy sources in high mass stars and how their structure changes, leading to a very special type of the variable stars. That's a very important tool for us when it comes to measuring the size of the universe. Now, we finally get to discuss the end of the high mass stars. We all know where this is going. Yes, we will be discussing supernovas. One example of this is a picture from the Crab Nebula. This is a remnant of a massive star that exploded in 1054 AD. In fact, this explosion was so bright that astronomers in China actually measured it. This is the first human-confirmed observed supernova. So how do we go from a big massive star to these giant massive explosions? Let's walk our way through it. So recall, the fusion reaction chains end with iron, right? If you're looking at here, this is a plot. On the x-axis, we're looking at the number of nucleons, number of protons, neutrons in the nucleus. So basically, as we go up this chart, we're going to heavier and heavier elements, hydrogen, helium, all the way up to uranium in the plot. And here we're talking about the average binding energy per nucleon. How much energy is in there when you bind together? So what happens is as you go up the chain initially, as we're going up the chain, as we're going to more and more nucleons, energy gets increased. The binding energy is going up. That means that as we start fusing these things together, more and more energy gets to come out. But then we reach that critical stage of iron, and it's this inflection point. If I was to draw a nice curve through it, let's make it purple. Come on, come back. Right. We have this curve. It's sloping and increasing. And then you reach this inflection point. There's that inflection, and it starts to go down. And I'm going to exaggerate a little bit. All right. So at the inflection point of iron, the binding energy now needs more energy in than what can be released by just smashing things together. So once you reach iron, degeneracy pressure isn't going to be enough. We're going to start collapsing the core, and things are going to go catastrophic. Because there's no more ability to feel all this weight that's on top of this iron core crushing down on it. Remember, think back to these onion shells. You've got this iron core, or once you run out of silicone, you're stuck at iron. You can't fuse anymore. So there's no more pressure here pushing outwards. All you have is the weight coming in from all these other shells that are still fusing. There's still enough thermal energy here that these outer shells can be doing some type of fusion. So you've got fusion, 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 and nothing to support itself. So the core starts to collapse. Core will shrink in on itself, and then we'll reach a critical stage where suddenly you can't collapse anymore. Fusion's not occurring. Something else has taken over. The fusion can't occur anymore, and it creates this shock wave that literally ripples through the entire star, destroying it. So let's go through this in a bunch of steps, all right? Eventually, electron degeneracy pressure can't stop iron core from collapsing. There's just so much mass there that we start taking this iron core and squeezing it down and down. The degeneracy pressure just can't hold it up anymore. So a couple of things start to happen. You're going to have thermal gamma ray photons. What do I mean by thermal gamma ray photons? Remember our idea of black body spectrum? The hotter an object is, you have those curves. Here. Curves like this, where you say that's the peak wavelength corresponding to a temperature of the object. So what's happening is that in this core now, the temperature is so hot that there is a peak wavelength in the short spectrum, and we're getting gamma ray photons. This core is getting so hot that it's radiating, oscillating in a thermal temperature equal to gamma radiation. So gamma rays are being created thermally, inside the core of the star. And what those gamma rays do? Well, they start obliterating the iron nucleus, literally obliterating it. It's called photodisintegration. This thermal gamma ray photon will hit an iron nucleus and just shatter it into a bunch of helium atoms. Alpha particles, you remember that name. On top of that, this pressure is also forcing protons to literally absorb electrons. The term I use is kind of this mutation is going to occur. Remember, protons positive charge, electrons a negative charge, stick them together, neutral, no net charge. So the pressures are so extreme that protons are literally gobbling up electrons, not electrons bounded to them. These electrons are not being bounded to protons. They're literally fusing together in a sense. So when those electrons and protons mix together, they go electrically neutral. So you get yourself neutrons flying about, and some neutrinos. Neutrinos, they try and stream out of the star. Remember, neutrinos don't really interact with a lot of matter. So neutrinos are streaming out, releasing a lot of energy from the core, and we're starting to get this dense neutron core. It was iron, but the iron's literally being obliterated because of how hot it is. And what's left there, those heliums, those protons, electrons, they're being forced together into neutrons. So this combination of photodisintegration and electron absorption eliminates any pressure that was supporting the core. And so the collapse of the core just continues faster and faster. We've talked about how all these different layers, core collapse was happening, temperature went up and pressure increased. But in all those previous examples, there was degeneracy pressure that could resist any further collapse. Because eventually, fusion would happen. Pressure would go up, fusion would happen. But there's no higher fusion chain. You can't get free energy. Not even a star can get free energy. So we've reached the end of pulling any free energy out. And so the core just continues to crack down on itself because there's no possible fusion chains left. Until eventually we've reached a stage where you can't squeeze anymore. And there's this sudden and violent flip of forces. The core shrinking, and then violently it becomes an outward force. It suddenly becomes repulsive. This sudden inversion creates a shock wave through the star. The flip itself is caused by neutron degeneracy pressure. Remember, we were trying to squeeze electrons before, and those electrons triggered helium fusion. Well, when we get to these hot thermal gamma ray photons, one of the products of fusing protons and electrons together is a bunch of neutrons. So this core is now what was a bunch of iron is now just a bunch of neutrons. Massive nuclei, these nucleons. And so you have this entire core of neutrons. They reach their own degeneracy pressure. And at that stage, the forces flip around and start pushing outwards. And you create this literal shock wave throughout the star. Some neutrinos are even literally trapped amongst this shock wave. Even the neutrinos can't get past this new type of force created by that neutron degeneracy pressure. That sudden flip creates this shock wave throughout the entirety of the star, bulging outwards, until finally you blast open into a Type II supernova. This giant, massive explosion. All the material of the star gets violently ripped, torn apart, and spewed out throughout the cosmos. All that remains of the star was that dense neutron star at the core. Remember, that core ran out of fusion at iron. That iron is obliterated and eventually left with neutrons in the core. And when that star goes supernova, you have this dense, what we now call a neutron star at the center. So all of this I've gone through in these last 8 slides is summarized in this one image here of the core collapse when you reach iron to eventually the flipping at neutron degeneracy pressure to that shock wave rippling out till you get the big, massive supernova explosion. Ready for some pictures of supernovas? So let's look at supernova SN 1987A. And I hope it's obvious by the naming convention. This was a supernova observed in 1987. Right? What I'm going to point your eyes to is over here. Flip the picture. And there is a supernova. This event, it was only a few minutes, and the radiant light could have been seen for days. The event itself would have been millions of times the luminosity of the sun when it occurred. We have so much data on this, so we actually have simulations of it. So let's try and pull up the simulation of this data, of this run. All right, here it goes. Big supernova. Materials being ejected outwards, creating this new cloud. This is going to form new nebulous of material. And here's simulation of it in 2017, creating this ring around it. All right, let this. It's going to loop around. All right. Supernova happens. Like I said, when that occurred, this thing was millions of times brighter than our sun. That much energy was released. So supernova is this very violent, bright incident. Here are some light curves to display what we mean by different types of supernova. And I'll point out here, we have type 1s and type 2s. And it's the curve of the supernova explosion itself that determines which categories we put it in. I'll trace out a type 1 specifically. Let's get this to a good color there. All right, so we're dealing with like a type 1 supernova. What's going to happen is that explosion happens, and for type 1s, remember this is like our low mass stars and binary companions. Type 1s, you suddenly skyrocket up in luminosity, tons and tons of energy is being released, and then it flips down and decreases. All the type 1s have this kind of pattern. Here's another type 1. Let's clear that. Here's another type 1. Follow the yellow curve here. Peak, and then gradual decline in the luminosity, the energy output of the explosion. Now if we switch to a type 2, you can get some very strange outputs. We'll follow this blue curve here. For a type 2 supernova, you have it going out, out, out. You reach a peak, and then you could have another peak later on. So you get this like flatten. The energy output is large for a long time period. We're talking on the x-axis, we're looking at days. We're looking at months after the initial bright part of the explosion. There's still tons and tons of energy being generated and released during this violent explosion. So the difference between type 1 and type 2 is basically the type of the curve that explosion releases. And now a key insight. Right? You look at the periodic table. Remember, fusion stops here at iron. So we have this entire region of the periodic table that we need to explain. We have this whole region of the periodic table to try and get to. And a lot of it comes from these supernovas. So let's go through this, all right? Hydrogen, helium, that came from the Big Bang, all right? Obviously, not all of this, but the majority of this. All right. Then you'll get low mass stars dying. Carbon, nitrogen, lithium. Think about our proton-proton chain, how you're getting heliums out. That helium can be later used to fuel some lithium and carbon chains, right? So low mass stars simulate these. And then our massive stars. When they explode, all of this material was tend to be produced inside their cores. And then you'll hit to cosmic ray, right, fission, merging of neutron stars, all these other higher level materials, higher order nucleons, they get produced during those gigantic violent explosions. So how we go above iron is due to the amount of energy that suddenly, remember, rippled throughout the core. The core gets that sudden inversion and violently tears apart the star. That violent tearing is the energy source to make some of these heavier elements, these heavier materials. Altogether, this is called nucleosynthesis, how I go from light elements to heavier ones. Right? Here's another plot to represent this. Basically, we're saying, look at the element number of protons in it, and the number of atoms relative to hydrogen that we find. So hydrogen is going to be number one. How much do we find of heavier and heavier elements? And you'll see this kind of chain of the heavier materials are, the fewer and fewer of them exists. Straightforward logic. Fusing hydrogen into this stuff, into this stuff, into this stuff. So as you go higher and higher, there's less predecessing material to make the next bits. So what's left over after a supernova explosion? What remains, right? Once again, it depends on how massive that core is. If that mass is less than 3 solar masses, you're going to have a neutron star. Just this dense neutron floating out in space. Technically, if you want to be semantic, star is not correct because there's no fusion happening. But the name is stuck. We call them neutron stars, and I will continue with that convention. Right? So these neutron stars, they'll have masses somewhere between 1.4 solar masses to 3, but they're going to be tiny objects. They're going to have radii of 10 or 20 kilometers. You could walk 10 kilometers easily in a short time period. So imagine something that is more massive than our sun and the size of your neighborhood. That's a neutron star. Very, very dense, heavy objects. Now, an interesting thing that can happen is, let's say we had a supermassive star that was part of a binary star system. Well, supernova happens, you're left with this neutron star, and you can have this interplay of this neutron star sapping material off of its companion star and ejecting it out. You create what are called pulsars. Right? So think back to our discussions on angular momentum. Remember we talked about the collapsing of a nebulous. This would have been section 7. We're asking, hey, what happens as a rotating nebulous gas cloud collapses in and shrinks in size? The moment inertia went down, the angular momentum goes up. The rotational velocity goes up to conserve that angular momentum. Well, the same principle applies to these neutron stars. Big mass shrunk down, inertia went down, it has to rotate faster and faster. So we have these rapidly rotating neutron stars, and that's what we call our pulsars. Basically what's happening is that this is creating huge magnetic fields that are ejecting tons of charged particles at its poles. As it's rotating, it's creating these magnetic fields that start sending charged particles radiating outwards in these gigantic jet streams. All right. The analogy we say is this reminds us of a light post. Right? You've got a lighthouse, and as that lighthouse sweeps by, you see the rays, then it rotates out of view. Then the rays sweep back into view. Similar idea with the neutron stars. We say, all right, as the neutron star rotates, we get a sudden spike in charged particles, a spike in the jet as it's pointed towards us. Then it'll rotate out of view and come back. So you get this pulsing as these neutron stars, these pulsars, act like a lighthouse in the cosmos. So we started this section looking at the Crab Nebula, and here's the Crab Nebula again, only this time in X-rays. Remember, this one was first absorbed all the way back in 1054 AD. And here it is in its X-ray view. So even with the star gone, there is still this glowing, energetic region of space. This ties back in to where we discussed what is the interstellar medium. We said, well, we live in a hot bubble of X-rays around us. Well, that hot bubbles of X-rays around our solar system most likely came from a previous star going supernova. Because here's the Crab Nebula, almost 1,000 years later, right? And it's still glowing in this hot X-ray energy. And that's being produced by that neutron star, or present at the core, the center of this supernova. So to end this section, we're going to do a brief recap of the stellar life cycles. We'll do low mass to high mass stars. So remember, you take this big molecular cloud, probably produced by a supernova. But either way, you've got this big molecular cloud that collapses down to protostars, and depending on the amount of mass, you become either a low mass star or a massive star. Low mass, right? It's less than 8 solar masses, and you can become a red giant when you leave the main sequence. If you're a lone star like our sun, that red giant will eventually, through a long chain on the HR diagram, turn into a planetary nebula, eject all of its surface material, and finally cool off into a white dwarf, just this hot, glowing core of carbon. And there's no fusion happening in here, so it's just cooling off over time and eventually reach what we have dubbed a black dwarf. This carbon core material that's now just cooled over the eons. However, if this low mass star was part of a binary star, there was 2 stars, you can create this interplay of the binary star and the white dwarf. Red giant dumping matter on the white dwarf, and you can get either a nova, right? Remember, red giant dumps material onto the white dwarf's atmosphere suddenly goes nova, and then repeats. Or too much material gets dumped on, and you get a type 1a supernova. Now for the discussion we just had today, you could have enough mass that protostar turns into a massive star, 8 solar masses or more. It will also turn into a red supergiant, but because of how massive it is, it will go supernova. And we talked about, well, what remains of this? We talked about the neutron star, and that neutron star, that core of neutrons, turning into a pulsar, rapidly rotating. Next time, we'll talk about how this will lead to black holes. With that, we'll call it in section 17. I'll see you all next time.